Okay, so let's say that we do some kind of um, aldol condensation, and let's say that we just bring these two together and heat this up with some sodium hydroxide and heat, right? So that we generate the enolate, right? And then we, come in, right? Some base comes in. And we end up with an alpha beta unsaturated ketone, right? Okay, fair enough. So let's take a look at this guy over here for a second. I'm just going to redraw it here. Let's say that we take this and we react it with everyone's favorite in here. Let's say we throw in a Grignard, okay? So, all right, well, we've got a ketone, we've got a powerful base, a powerful nucleophile, far more likely to act as a base, though, right? But, right, in this case, we don't really have any super acidic hydrogens. I mean, I guess we could, deprotonate, make another enolate, that kind of stuff. But what's going to happen is we will end up having the Grignard attack at the carbonyl carbon, right? And if we finish up with an acid workup, there's going to be our product, okay? All right, nothing too unusual there, right? We've seen this happen before, okay? And if we take this same product, or excuse me, if we take the same starting material here, and now we use our softer organometallic, right? So let's say that we instead use our copper lithium salt there, okay? Now remember we said that these copper lithium salts are going to behave a little bit differently. The way they react, how nucleophilic they are, how reactive they are, it's going to be a little bit different, right? And so if we do that, what we will get is this product here. And, we'll have to come back and clean things up with acid, right? Okay, that's fine. Interesting. Okay, so what is going on here? Well, let's try and explain this, right? So if we just look at our starting material, I'm going to just, I'm going to try and just draw it here a little bit bigger. You could just zoom in on it. Yeah, I know. So obviously, if we have a nucleophile, like the Grignard that comes in, it's going to attack here, okay? Because we know that that's got a partial positive charge. We know that we can form a resonance structure, okay? We know that we can form a resonance structure wherein we can put a negative charge here, okay? And a positive charge there, right? So that carbonyl carbon is feeling pretty darn positive. Well, that's not too unusual. We talked about that a lot when we first introduced the idea of carbonyls and their reactivities. But watch. If I bring that double bond over here, okay, if I bring that double bond over there, I can also put a positive charge onto my 4 position, okay? So 1, 2, 3, 4, okay? The beta position. I go back to my other video where I told you guys what the alpha and the beta and all that kind of stuff is, right? So through resonance, I can also put a positive charge on that 4 position. And that is actually going to be our, what's going to dictate some of our reactivity here, okay? Now, from the example that we did before with the copper lithium versus the Grignard there's got to be something said about the strength of the negative charge that's coming in, right? And the terminology that we would use with that, especially as you progress on to some of the upper division chemistry courses, would be softer versus harder versus softer bases, right? We talked about this a bit in Gen Chem, and you'll talk about it in Biochem for sure, right? But you'll talk about hard, soft, acid, base theory, right? Not every negative is as negative, right? And we already know that, right? You guys have already discussed this a little bit, okay? So depending on how negative something is, we can make it attached to the 4 position or the 2 position. And in both cases, that can be useful, right? It just depends on what you want to, what product you want to make, okay? Now, when we're talking about additions at the 4 position, right? When we're talking about additions at the 4 position there, right? We would call this a Michael reaction, okay? And Michael reactions are just an example of conjugate addition reactions. So if you type in, there it is. If you type in Michael reactions, you'll see there's quite a bit of literature about these. These are very important, okay? These are very useful for us. That means we can, we can bring in, and make carbon-carbon bonds at the beta position to a carbonyl. Extremely useful reactions for us, okay? And so there's a lot of it out there, and we'll talk a little bit about it here. And the internet is down at the moment now, but hopefully by the time I can post this and everything kind of comes back up, then I can, I can post some other links for you guys about Michael additions, okay? But there's 2 things we need to have, right? We need to have a donor, aka the thing that's going to attack at the 4 position, the incoming nucleophile, right? And we're going to have the acceptor, aka the alpha-beta unsaturated ketone. Now, in reality, right, everything's going to work in the same way that we just described. So what I mean is this. So if we have a generic structure, okay? Let me just make it as generic as I can. If we just have a generic structure, what we're looking for is to be able to put a positive charge at that 4 position through resonance, right? This is the resonance that we just talked about. This is what we just showed on the previous discussion that we had there, right? Excuse me. So if we're in a situation where we can use resonance to put a positive charge, in a series of pi bonds, okay, then we can call that a Michael acceptor. Now, it's not going to happen in every case. We're going to need some kind of electronegative atom, okay, to handle that negative charge, right? And we're going to need to have a system of conjugated pi bonds. Remember, the pi bonds need to talk to each other, otherwise we can't draw the resonance structures. If we can't draw the resonance structures, then we can't accept in a nucleophile. Here's what I mean. So, acceptors, okay? We can see this happening with ketones, okay? We can see this happening with aldehydes, right? In both of those cases, we can, do the same kind of resonance. Esters, okay? Amides, cyanos. Let's just do it like this, okay? And these are probably the most common ones that we'll end up seeing, right? Carbonyls like ketones, aldehydes, esters, amides, and cyanos, right? We can all draw resonance with these, right? Right? We can all draw a resonance structure with these to put a positive charge there at the beta position, right? At the 4 position. And so it might be good practice for you guys just to, kind of go through and prove this to yourself, right? Now, why did I choose these? Are these the only ones? All this? No, right? These are the most common ones that will... Well, I should be careful. Maybe not the most common ones, right? This is a good listing of what we can do, right? Really the point is, how can we figure out what an acceptor is on our own? And, right, we'd want to try and draw a resonance structure for us, okay? On the other end of this, right, we would want to ask, well, what can be used to come in as our nucleophile, right? Those would be our donors. Let me just draw a different color here just for argument's sake, I guess. Because we said that a Grignard would be too strong to do this, right? It would just go after the carbonyl carbon, right? But our copper lithiums, right? Those would be good donors, and we've talked a lot about those. We know how to make them. We can bring them together. We know about their limitations. We know how they react and when they react, all that kind of stuff, okay? But resonance-stabilized enolates are going to make good donors, okay? So if we have a series of enolates, okay, that are resonance delocalized, and we can even bring in nitro groups here, right? Remember we talked about how nitros are deactivating, they suck electron density, right? The same thing's going to happen to an extent when they're on alkyls here, right? So if we have resonance delocalized or softer negatives, right? In all these cases, we can draw a resonance structure where that negative is spread out over many different positions, okay? And that's going to be the key here. We can't have a strong localized negative charge. We need to kind of have it dispersed out. But if we bring those two together, then we can start to clip together the donor and the acceptor, and they're going to add at the 4 position, okay? So, right, whenever you guys see a alpha beta unsaturated ketone, right, we know that we can add right? We will add to the 4 position. Okay? Really, really useful. Really useful. Because now we know how to set up a situation where we can add at the 4 position, right? We could add at the alpha position. We can add at the carbonyl carbon, right? Under differing conditions. Like, let me just put some color coding here. Under different conditions and under different setups, we know ways of adding groups to either the blue, the red, or the purple carbon. And even if we wanted to be super duper clever, which we do, right, we could even add here to the yellow, right? We could add to the green there also in some cases, right? We know how to do a lot, and this is where it starts to get tricky in the second semester of organic chemistry. Because the question is, do I expect you guys to know how to add to all those different positions as selectively as possible? And the answer is yes, right? So we're paying attention, we're watching, we're thinking, we're looking, we're keeping track of this, we're practicing, right? All these things, okay? And now we know a new way of doing what's known as a Michael addition, where we can add alkyl groups and even bring in different functional groups, right, to the 4 position or the beta position, the purple labeled carbon there, of these carbonyl systems. All right? Okie dokie. So that's all I wanted to talk about in this video here. There's a nice little chunk for you guys there. Now we've talked about a lot of reactions, right? We've talked about a lot of reactions in this chapter, and that's pretty much the bulk of it. I might come back with one more video just to kind of clean some things up. But in reality, this is pretty much all what we wanted to talk about for this chapter here. Okay? All right, so I may see you guys with another video on the carbonyls here. I'll post an announcement I'll post an announcement for sure once I kind of decide what I want to do here. All right, but hopefully everything's going well with you guys. It's near Easter, so I hope everything's going well for you guys, and have a happy Easter. And I will see you guys soon.